Halo? Dzień dobry. Dobry wieczór. Super. Czy dobrze mnie słuchać?
Chyba tak.
Okay.
Możemy właśnie.
Okay. I'm gonna switch to English. So that I believe the conference is in English. Anyway, I'm extremely excited to be part of this conference. I would like to thank the organizers for accommodating the presentation so early in the morning, in your time, and in the evening, in my time. I had essentially two choices. The first one was to do it late in the evening or to do it early in the morning. As Mikołaj, who is, I assume, in the audience, is he there? As he knows, I'm not a morning person, and thanks again for accommodating me in the evening. I usually go to bed very late. It's almost midnight, and I live here in Los Angeles, just a few miles away from a NASA Jet Propulsion Lab, which is a prominent robotic exploration institute that probably many of you have heard. I'm excited to be part of this for a couple of reasons. First one, the space mining is very dear to my heart. I've been doing it for close to 20 years. I actually grew up initially in Katowice. I left for South Africa when I was a teenager and spent a couple of years working in the coal mines, in gold mines and diamond mines. I was actually the deepest mine in the world, 12,000 feet down, 4 kilometers down for a couple of months. My journey moved me from deep gold mining and coal mining to space mining. Sort of a similar industry, but obviously, as you can see, environment is going to be so much different. Secondly, I'm excited because I looked through the agenda, and there are a lot of folks that I met before and collaborated. Mikołaj Prucinski in particular. Hopefully he's around, but we went to primary school together. We went camping. We've been buddies for a long time, and it's amazing that 20 years later we come together in a full circle in a slightly different occasion. I never realized in my life that our path would cross again, but this time when talking about space mining. Karol Severin, he's probably also in the audience, I hope. We've been collaborating a couple of times, and our path has crossed a few times at the conferences and the meetings. And Gordon Wasilewski, who is, I believe, a coordinator of the conference as well, he actually stopped by my office a couple of years ago here in Pasadena. So anyway, this is super exciting. Again, thanks very much for accommodating my presentation, and I'll start on this. But space mining is one of the two things that excites me every day, that gets me out of bed every day. The second one is search for life, which to some extent is also linked to space mining. Slightly different applications, but these two things, space mining and search for life, are two things that I'm doing it's essentially my work and it's my hobby. So today I'll talk about mining water on Mars. And tomorrow, we actually starting on this project. What you see here is a rover. It's a JPL developed rover, and with the water mining system. And that's one of the things that we're going to be building in the next couple of years. So hopefully, as this conference kind of progresses every year, I could give you updates how we're doing. So why space mining and why in situ resource utilization? That's one of the things that people are always asking, and they're thinking it's all about getting rich, mining platinum on asteroids and so on. It's more than this. Imagine you are driving from Los Angeles to New York, and there are no gas stations on the way. And in fact, there are no gas stations in Manhattan. So this car that you see right in front of you would be loaded with fuel. There would be no space for anyone else except the driver, and everyone would be fueled. So it would be obviously a fun trip going on your own. So imagine that there is a gas station in Manhattan. So now you don't have to drag all the fuel with you. You can bring your girlfriend or your boyfriend or kids and dogs and so on. So now the trip becomes more enjoyable. In the same respect, ISRU, when you think about ISRU, it's all about cutting down on something that you don't really need and bring something that's highly valuable to you. And at the end of the day, in situ resource utilization or space mining, it's about money. It's as simple as that. If we had infinite amount of money, we wouldn't worry about space mining. But obviously, we don't. So to make space exploration viable, we obviously have to think how to do this. In particular, for Mars, there is something called the gear ratio. It's a ratio of how much mass we have to launch from Earth versus how much mass we can actually land on Mars. So if you boil it down to 1 kilogram of something on the surface of Mars, to send it back, you have to launch something like 226 kilograms from Earth. So if you have humans on the surface of Mars and you want to send a ton of water, you'll have to pretty quickly, the space exploration or Mars exploration will become very expensive. So now, if I can mine 1 ton of water on Mars, I don't have to launch all 226 tons from the surface of Earth. So it's all about, at the end of the day, it's all about money. It's all about making space exploration feasible, essentially, in our lifetime. And companies like SpaceX, if you actually see what they're doing, the company is extremely innovative, right? They're landing their own rockets and so on. It's all about cutting cost. It's all about cutting cost. Nothing less, nothing more. So, especially when it comes to Mars, this is what SpaceX and obviously NASA has been talking about for a long time. This picture is not going to be feasible without space mining, without mining resources on the surface of Mars. And the 2 most important commodities is obviously water and oxygen. If you have those, you can pretty much get 90% of everything else that requires these 2 commodities. And your market is oxygen and water. That's obviously to support humans or Martians. You also need propellant for journey back home. So here you have methane and oxygen, and methane you get from a Sabatier reaction where you have CO2 and water to form methane. And you can also use oxygen and hydrogen in a fuel cell to provide energy, especially at night or in the long winters. Obviously these winters are pretty severe. And obviously for agriculture, you need water, you need oxygen, and a bunch of other stuff. So this picture, again, is not going to be feasible if you do not mine resources that are present on the surface of Mars. Fortunately, Mars is sort of like Earth. It's got a lot of stuff, and a lot of stuff that's very similar to what we have here. We have liquid water. It's been confirmed, probably 100%, almost 100% confirmed, that there is a liquid water on the surface of Mars right now. There is obviously pure ice. There is also ice-cemented ground, or ice with a significant fraction of soil in it. We also have hydrated minerals in 2 forms, gypsum and clays, just examples of two of those. There is also water in regolith at a very low concentration, and you have some water in atmosphere, but that's very, very low concentration. So I'm going to go through a couple of those and discuss how we would mine water from these couple of these different resources. Let's look at liquid water. Last year, a European Space Agency ExoMars mission, the radar instrument called MARSIS, discovered that the hypersaline lakes underneath the southern polar ice cap, and they are approximately a mile deep, so not that deep, and they hypersaline, so they approximately somewhere between -74 and -10 degrees centigrade, so they super, super salty. But it exists. It exists. You don't have to mine ice. You don't have to melt it. You can essentially drill a hole and pump this water out to the surface. And can you do this? Well, we've done it, and we're doing it every single day. On the left-hand side, what you see is a picture from Lake Vostok in Antarctica. It was a Russian base, and still there. The Russians drilled 4 kilometers down, and they poked into the lake, and they managed to capture some of this water from the lake. It was also it is still the coldest place on Earth at -19 degrees. So it took 20 years to do this because of different issues, technical and political, but we've done it. Also on the Devon Island in the high Arctic, actually I've been there a couple of times. Just recently, also last year, we found 2 hypersaline lakes at half a kilometer down, so not very deep. And these lakes are at approximately -10 degrees centigrade. So these, especially the one of these lakes in the Arctic, would be fantastic a venue for doing field testing prior to sending anything to the surface of Mars. And if you consider that Mars is a third of the gravity, and the 500 meters on Earth is equivalent to 1.5 or 1 mile on the surface of Mars. So if you can drill down into these lakes in the Arctic, there is a high probability you can do this actually as well on Mars. If you look how we do the drilling right now in Antarctica or in the this is a wireline system. This drill essentially suspended all the motors, anti-torque actuators, and coring bit is suspended as a tube. It takes a couple of months to drill down to 2 kilometers. It's obviously not automated. It's not a robotic system. There is a lot of human labor involved, but this data essentially shows that we're doing it pretty much every single day in Antarctica, so it's feasible. I've developed drills like this here with Honeybee Robotics. This is our wireline system called Planetary Deep Drill, and we tested it in a gypsum quarry. We drilled down to 10.5 and 13.5 meters within literally a couple of weeks. The drill is on the right-hand side. It's a slim tube, something like 2 inches in diameter, for just over 4 meters long, with integrated instruments and the cameras. So this demonstration essentially showed that wireline system could potentially be deployed, robotically in rock. And in next month, actually flying to Greenland to deploy this drill that's on the right-hand side. We are going to be drilling 120 meters robotically. As a demonstration that we can actually get down to 120 meters, fully hands-off, no human intervention. And as a first step to drilling in the Arctic into these glaciers, that are overlaying deep lakes. So hopefully we're not gonna get stuck, and hopefully next time we meet, I'll be able to tell you how deep we went and all the stories from Greenland. We're actually gonna be right in the center of Greenland, in a place called Summit. It's around 11,000 feet, so it's pretty high altitude. Fortunately, it's still cold, so we don't expect any liquid water going down our boreholes and freezing literally in place. But this kind of system is feasible. We put the drill on a Curiosity-sized rover. You can see the two pictures, and dimensions, the mass, everything checks out. So using existing entry, descent, landing technologies, using existing rovers like Curiosity rover, deep drilling on the surface of Mars would be possible. Let's shift gear and talk about pure ice. In 2008, Mars Phoenix, for the first time, landed above layers of ice. And a few decades ago, we were thinking that there is ice, and in 2008, we actually landed on ice. If you look at the insert, the small photograph at the bottom left-hand corner, what you see is patches of ice. This is absolutely pure ice, which is actually very salty. And it was right near the surface. And on the right-hand side, what you see is SCOOP, which is called Icy Soil Acquisition Device. That's something that we built here at Honeybee. And for the first time, this digging and drilling system touched ice on another planet. So this was very rewarding, and this was the first step to space mining. We didn't drill very deep. We drilled maybe a half a centimeter or centimeter into the ice. But as you know, long journeys start with the small steps. And for us, this was a very small step. And obviously, next step is going to be much bigger. It was exciting mission. So as we start looking at the data coming back from Mars, we discovered that, in fact, there are layers of pure ice buried under a couple of meters of regolith closer towards the equator. So Phoenix is up north. It's just too cold, and every winter you have a couple of feet of carbon dioxide being deposited on the lander, and so you can't really do any surface operations. But if you go further south, maybe 30, 40 degrees north, into places like Arcadia Planitia, you can actually survive. It's relatively warm, it's relatively flat. You have a lot of atmosphere above you, so you can slow down during EDL. And in these locations, you actually have plenty of ice in a near subsurface, within literally meters to 10 meters below the surface. The picture that's right in the center, this is a picture taken from one of the Mars spacecrafts, and it shows a couple of meters of regolith, and there's something like a 50 to 100 meter thick ice layer. It's unbelievable that we are finding pure ice on the surface of Mars so close to the surface. So Mars is getting very, very exciting. So how would you do this? How would you mine ice if you could? We actually doing it. This is a South Pole base in Antarctica, and it's occupied throughout the year. There's probably 10 people wintering over, and a few hundred people during the summer, and obviously they need water. And up to a couple of decades ago, they had the bulldozer driving around, picking up snow, and they had the snow melter that would melt snow and create water. But one day, this smart engineer called Rodriguez said, hey, how about poking a hole below the ice, melt the ice underneath, and pump it to the surface? And this, what became known as a rod well, has been providing liquid water to this base for over a decade now. And the idea is that you are pumping warm water to the surface, you're taking some of this warm water, you go through a steam generator, you're heating it up, you're pumping it back into the subsurface, and you're checking it to form a bigger cavity and melt more water. And slowly, you can see these sort of layers. The entire cavity gets bigger and bigger and bigger, and your water pump is being lowered further down. So this thing works. It works every single day. So that's a reason why we decided to use this technology and develop a red water system. It's based on a cold tubing. So the drill is essentially a tube on this drum, and as this tube pulls out, it forms a relatively rigid drill pipe. And at the bottom of this drill pipe, you have something called bottom hole assembly, which is tightly integrated electric motors with heaters, with pumps, with water jets. So you can drill down until you hit water or ice layer, and at that point you stop. You heat it up, you rotate the drill bit, you melt water, and you pump it to the surface. And the project that we're starting right now is going to develop this entire scheme. So it's a very exciting project. So let's look at the ice-cemented ground. How would you do that? So first thing about ice-cemented ground to realize is that the icy soil is as strong as concrete. And to convince ourselves this is so, what we did is we took unconfined compressive strength machine and we prepared a couple of samples. These samples had different water weight percent, 3, 5, and 12. And they also were tested at 2 different temperatures: cryogenic temperature, 77 Kelvin, and at relatively warm, sub-freezing temperature, 253 K. And what we found is that at the lowest temperature and with the lowest concentration, around 3%, the strength is a couple of MPa. And that couple of MPa is actually the strength of a sort of commercial brick that you're using to build houses. If you increase the water concentration in the soil and you drop the temperature, at that point you get to something like 40 MPa, and that's a strength of commercial concrete. In fact, 40 MPa is the strength of Indiana limestone, which was used to build Empire State Building. So if you've ever been to Manhattan and you're wondering what an Empire State Building is made of, it's made of Indiana limestone, which has 40 MPa strength, which is exactly the same as the strength of an icy soil at cryogenic temperatures. So how would you do that? Well, what you see here is a percussive scoop. What we decided to do is we looked at what different industries are doing, and different industries may have jackhammers. So we thought, well, why not putting a scoop at the end of a jackhammer and see if we can essentially scoop a bit of this icy soil. This scoop got stuck. Just for reference, we were pushing with something like 600 pounds or 3,000 newtons, and we barely got maybe a centimeter into this icy soil. So we knew that if we try to do this, it's not going to work, and that's our stuck scoop on the right-hand side. And then we took a hammer drill, like a Home Depot commercial hammer drill, and we made this hole literally within a couple of seconds. We realized that drilling can penetrate icy soil, but the sort of like percussive scoop or trying to jackhammer this thing, it's not going to work. So now the question was, how would you mine water if you were to use the drill? And for that, we developed something called planetary volatile extractor system. It's essentially a coring tube that has heaters on the inside. So the idea is you deploy it on a rover. On the top left-hand side, you have what you see is a 500-pound resource prospector rover with our drill on it. You drill down, say half a meter or a meter down, you create a core, you heat it up with your heaters on the inside, the water sublimes away, is driven off and goes up through the slip ring and swivel assembly to your cold trap on top. And in fact, we did some tests, and this is actually hardware integrated on the rover and inside the vacuum chamber. It was powered by one of our drills with rotary percussive system. We had to make sure that the force required to drill is less than 100 newtons because of the rover requirements. So we put this thing in a vacuum chamber. We drilled into different formations, and we managed to mine some water. And what you see in a top in a small picture, it's actually my hand with a glass of water. And somebody from NASA said, "Hey, how about sending volatiles straight to the mass spectrometer?" And we thought, well, let's try it out. So we put this Mylar bottle, that's bottom left-hand side, and we filled it up within a minute. So mass spectrometer is an instrument, if some of you are not familiar with that instrument, that essentially measures concentration and elemental distribution of material. It tells you whether you have oxygen, it tells you whether you have calcium, and to some extent it can tell you the concentration of this. It can also do isotopes. So the folks from NASA were scientists, and they thought, well, this PVAX is not only a water extraction system, it's a water vapor or volatiles extraction system. So maybe we can use it for providing volatiles directly to the mass spectrometer. And that's actually something that we had discussion with NASA this morning, and they asked us to speed up development of this technology, because maybe we're not going to send it to Mars yet, but it's probably going to go to the moon in the near future. Now, moon is super hot. Everyone's talking about moon here in the US. So let's look at the minerals. Gypsum. There's plenty of gypsum on the surface of Mars. And those of you who had broken bones and they had to put a plaster, they know everything about gypsum because they had to carry gypsum with them when the bone was healing. The anhydrite is essentially dry dry mineral that does not have water molecules. So if you take a calcium sulfate and strip it of 2 water molecules, you're going to get anhydrite. So on Mars, you have gypsum. And this 2 water molecules is actually a significant fraction of water. It's something like 20 or 30%. And gypsum is relatively weak. So on Earth, what we do is we drill, and we're essentially doing drilling and blasting. So we drill these deep holes, we put explosives, we blast it out, and then a truck comes in, loads it into some kind of a transportation system. It goes through a crushing and milling process, goes through a calcination process to extract essentially hydrite, and water is normally recycled and dumped somewhere else. But for us, water is a resource. So we looked at, we actually got funded with folks at Michigan Tech, Paul Fonsasanta, and we started this work last year. The idea here is that we would use sort of like a water jetting system to crack through the gypsum and dissolve it in situ, and then we would pump the slurry straight into a calcination process, extract water, and pump some of this water back into the water jetting system. And we start doing this. What you can see on the left-hand side, it's a video that shows water jetting, and it actually works pretty well, again, thanks to the fact that gypsum is relatively soft material. And on the right-hand side, this is a benchtop calcination process. We essentially recovered 16 grams of water, which is just over 70% of the recovery. And that's really, really And looking at regolith, there is a bunch of ways to do this. On the top, there is a rover called Razor, developed by NASA Kennedy Swamp Works with Rod Mueller. This rover has two drums on the opposite sides. So by utilizing these two drums at the same time, the rover essentially becomes force neutral. And that's very important if you're working in a gravity field that's relatively low. In the middle, what you see is a sonic/percussive scoop that we have developed for cutting through soils. Although percussive scoops are not very good for cutting through icy materials, they're actually extremely beneficial when digging into soil. The forces required to dig into soil using percussion are somewhere like 10 to 100 times lower than if you were to using static scope. And then down below, what you see is a pneumatic mining system. It's a small rover, the size of your laptop, that uses gas to actually mine. But instead of a vacuum suction, like in a traditional household vacuum cleaners, what we do is we bring a small amount of compressed air to send a puff every so often and move the soil from the ground all the way to the container. And we did a lot of pneumatic testing. With essentially 1 gram of gas, we can mine up to 6,000 grams of soil. And right now, we have something like close to 10 different pneumatic projects at Honeybee. And one of these projects includes a pneumatic sampling system that will be part of a JAXA, Japanese Aerospace Agency, Mars Moon Explorer mission. It will essentially capture the surface of Phobos and for sample return. The mission is going to launch in 2024. Samples will be coming back sometime in 2029. So that's an exciting mission that is going to use this sort of pneumatic mining system. And I want to end with this picture. We have been involved in a very, very fascinating robotic competition called ICE Challenge. It's hosted by NASA Langley every single year. I've been involved with this right from the beginning, and we've been sponsoring this competition. You have something like 10 teams coming to NASA every single year, sometime around June, and they bring their drilling systems, water mining systems, and the goal is to drill down through a foot or maybe 2 feet of rocks and dry soil, get into ice and try to pump it up. And on a very first year, most of the team fails. Actually, pretty much everyone failed except one team. One team managed to get something like maybe a gram of water after 2 days or 3 days of work. And they came back next year, and next year there were probably 3 teams or 4 teams that actually managed to mine some water. So as the team learns how difficult it is, they're improving their robotic systems. But it's super exciting, and this competition does 2 things. First one is obviously it develops technologies, and second one is develops future space mining people. So these are space miners that you see in a picture. Sooner or later, they're going to develop mining systems that will go to Mars, to the Moon, to the asteroids. So that's super exciting. And I want to end with this picture. I'm always excited to go out to the field, and that's me on the left-hand side in dry valleys of Antarctica. What you see here is a 2.5 meter of a drill pipe. We essentially took us 2 hours to drill through this ice, sort of straight underneath us, and it was just fantastic field deployment. And I'm looking forward to the Greenland in a couple of weeks. So with this, I would like to open to questions, if there are any. Maybe Mikołaj will have some questions.
Thank you, Kris. So, do we have any questions from the public here?
Actually, Mikołaj texted me. He's driving.
It's a shame. For now, we have no questions, so I hope we'll have some in the future. But thank you very much.
Okay, sounds good.